Hello everyone, Mr. Fawcett back here with part 2 of lesson 2.2, definition of a derivative. So in part 1, the last video, we worked our way towards the definition of a derivative. We know that there are multiple forms. I put both of those on the screen. And today we're going to use the definitions to answer some problems. There's a couple of things I want to talk about before we jump right into the problems. One, let's review the two definitions of the derivative. Both of these in the blue and pink are able to be used. Just sometimes one is easier than the other. And this is what I want to kind of get into. So the pink is going to be used when we want to find the general derivative. So just like functions, and I guess there's one more thing I should add. We'll keep this part separate from the graph for now. Actually, you know what? We'll keep the graph. Okay, so just like a function, I can have f of x equal x squared minus 4. I can also find the specific value of a function at a given x value. So I could find f of 5, right? And that gives me 25 minus 4, so it gives me 21. So you can have the general function can be evaluated at any given x value that's in its domain, and you can have the value of a function for the specific x value. So when I'm talking about the pink and I say use that when finding the general derivative, that's what I'm talking about up here. When you want to find the general derivative, the derivative function that can be used to find all the specific derivatives, you may just want to use the pink for now, okay? I think that's easier. You can certainly use the blue, and you may be able to experiment with that and see if you get the same answers when you use the pink. But for the sake of this video, we're just going to use the pink function when we want to find the general derivative. When you want to find the derivative at a specific point, so while the general derivative, actually let's talk about the blue first. So if I want to find the derivative at a specific point, that would be like taking this function here in blue, and we'll call it g of x, keep it different from our f of x. Let's say you want to find the derivative at this point, we'll call that x equals 3. Well, we know that's the slope of the tangent line at that point. That's going to be our derivative value. But this slope would be equal to g prime of 3. G prime of 3 would give you the derivative, the slope of that specific tangent line. Now, you may not want just the slope of that specific tangent line. You may want to come up with a function that could give you the value of any tangent line you could draw on that function. So the derivative of the function, or the general derivative, would just be g prime of x, where you could substitute in any value on this blue parabola. You could substitute in any x value into g prime of x, and it would give you the slope of the tangent line. So just like functions up here, where you can have the general function, and then you can have the value of a function at a specific point, derivatives work the same way. You can just have the derivative function, and then you can have a specific value of that derivative function after you've substituted in a specific x value. So when we're doing something like finding the derivative function, we're going to use the pink definition of the derivative. When we're finding a specific value when we're finding the derivative for a specific x value, we're going to use the blue definition. Again, just keeping it, we're keeping it consistent across the board for this video, and that's because I think those methods or those definitions are the easiest for those specific problems. But you can use both for either type of problem. Okay, let's get into our first example. We'll get through as many as we can. So it says use a definition of a derivative to find the derivative of the following functions. So let's look at number 4. I've got my derivative f prime of x. That's going to be equal to the limit as h approaches 0 for f of x plus h minus f of x all over h. That is going to be equal to f of x plus h is 2/3 x plus h plus 3. So again, f of x plus h just means I'm substituting in x plus h anywhere I see an x in the original function. Then I'm going to subtract f of x. So subtract 2/3 x plus 3. Make sure you put parentheses or brackets around the entire function you're subtracting, otherwise your signs will be messed up. And this is all over h. And make sure you don't forget your limit expression like I almost did, because we're still evaluating a limit. So we're actually going to be using some limit rules or some limit properties as we try to simplify this expression. Now, if you were to substitute in 0, right, that would be our direct substitution as the first step in the limit process. I'm going to do this once, and then I'm not going to do it for the rest of the problems because it works out the same way for every other problem. So if I substitute in 0 for h, I get 2/3 x plus 0, which is x, plus 3, minus 2/3 x minus 3 over 0. And this gives me, you can see that our numerator terms simplify out. So we're left with 0 over 0, which is indeterminate. So again, all this tells us is that this limit, we may be able to find the value of it. We just can't do it this way. So when we run into indeterminate forms, right, if we go back to that flow chart, there's a couple different things we can try. We can try factoring. We can try rationalizing either the numerator or the denominator if we have some radicals. We can try some trig substitution. Here, let's first try to multiply out and see if we can simplify anything. And then maybe we can factor something out of the expression. Namely, we'd like to get rid of this h from the denominator. We'd really like to be able to factor out an h. So let's erase what we just did here. You guys can keep that on your paper. I just need the space. And I'm going to multiply out the 2/3 to the x and to the h. So I'm going to keep my limit. And I get 2/3 x plus 2/3 h plus 3 minus 2/3 x minus 3 all over h. If I then simplify out my numerator, 2/3 x and negative 2/3 x simplify, 3 and negative 3 simplify, and I'm left with the limit as h approaches 0, of 2/3 h over h. Well, we can simplify this one more time, right? The h's simplify. So I'm left with the limit as h approaches 0 of 2/3, and the limit of a constant function is always going to be equal to the constant function's value. So the derivative here is 2/3. And if you're unsure of why it's equal to 2/3, right? I just got done saying the limit is a function. Well, 2/3 is a function. All this means is that the slope at every single point on the function is 2/3. And I'm going to pull up the calculator just to show you what I mean by that. Okay, so I have my function entered into my calculator. We should understand that this is going to be a linear function, which it is. And if it's a linear function, well, the slope is constant. So if we found the slope for one piece of the function, right, if I just pick 2 points on this function and I use my slope formula, it's going to be the same as whether I choose these 2 points on the function, right? The slope is going to be the same. So for a linear function, the slope is going to be the same everywhere, which means the derivative is going to be the same everywhere, which means the derivative is a constant function. So it doesn't matter what value I choose for my tangent line, the derivative is going to be the same. The slope is going to be the same. And you can see that, right? If here's my tangent line for that point, here's my tangent line for this point, here's my tangent line for this point, and here's my tangent line for this point. The tangent lines all have the same slope. So the derivative is a constant function here. All right, let's go back and look at the second problem. So we have g of x is equal to negative x squared minus 4x plus 1. I'm also going to run out of space, so I'm going to cross out this problem because I may need to use the whole page. I'm actually just going to start over here. So the limit as, well, you know what? Let's write out what we're trying to find. We're trying to find g prime of x, so that's equal to the limit as h approaches 0 of g of x plus h minus g of x all over h. So g of x plus h is going to be negative quantity x plus h squared minus 4 times the quantity x plus h plus 1 minus the entire g of x function. Okay, all over h. Now, oops, guys, you got to keep letting me forget this limit. Of course, it's completely my fault. Okay, I don't want you to forget. I'm making a big deal out of it because if you leave that off of your paper, you would lose some points. So again, like I said before, I'm not going to go through the process of doing direct substitution. This is going to come out as an indeterminate form. All right, so we do need to do some factoring here. But first we are going to multiply some of these expressions out before we do that. So limit as h approaches 0 of negative x squared plus 2xh plus h squared, and you can check my, I don't like to call it foiling, but in this case it is because it's a binomial, minus 4x minus 4h plus 1 plus x squared plus 4x minus 1. I'm going to distribute that negative sign. Of course, this is all over h. So the limit as h approaches 0 of negative x squared minus 2xh minus h squared minus 4x minus 4h plus 1 plus x squared plus 4x minus 1 all over h. Now again, we're going to do some simplifying here. I've got a positive x squared, I've got a negative x squared. I've got a positive 4x, I've got a negative 4x. I've got a plus 1, and I've got a negative 1. And that's all we can simplify out for now. So let's come up here. I'm going to have the limit as h approaches 0 of negative 2xh plus h squared minus 4h all over h. Now, again, our goal here is to eliminate the h's by factoring and simplifying. So it's nice because each term here has an h, which means I can factor out an h from each term in the numerator and simplify with my denominator. You could do the in-between step where you have h and then inside parentheses minus 2x plus h minus 4. I didn't write that step initially because I think we know how to factor by now, but certainly feel free to write that out. And then you could simplify. And I think I misspoke before. We're trying to eliminate the h in the denominator, not necessarily the numerator, because we can't have a 0 in the denominator. But if we have a 0 somewhere in the numerator, that could be okay. Once we have simplified out the denominator, we're left with the limit as h approaches 0 of negative 2x plus h minus 4. And we can try direct substitution again. So I get, and these should all have equal signs. So I get the limit no more limit once I use substitution. So I get negative 2x minus 4. And remember, this was our g prime of x. So in this case, we don't have a constant function. Our derivative is going to change based on what our value of x is. And if we graph this function, so I will pull that up and meet you over at the graphing calculator. So I have this entered. I'm going to hit the graph button. And this makes sense, right? Our derivative is not going to be a constant function because at different points on this graph, the tangent line does not have the same slope, right? If I just pick 2 points, it's clear. These two tangent lines have different slopes, so our derivative is going to be a function of whatever our x value is, right? If I substitute in negative 3 for x in my derivative, right, and my derivative was g prime of x is equal to negative 2x minus 4. If I substitute in negative 3, I'm going to get 6 minus 4, which is equal to 2. And 2 looks like the slope of this tangent line, right? Same thing if I substitute in 0. If I do g prime of 0, that gives me 0 minus 4, which is equal to negative 4. And that could certainly be the slope of this tangent line, just based even on how it looks. So in this case, our derivative was a function of x, and it depended on what x was to what we would get for the value of the derivative. The first problem we did, it was still a function of x, but because it was a constant function, it didn't matter what x was. It was still going to be the same derivative value regardless. Okay, you know what? We're going to stop there because we're almost at 20 minutes. We will do a part 3 for this lesson where I go over 1 or 2 more problems because there are a couple different types. There are a couple different types of problems in this practice section, and we really only touched on the first type. All right, until then, this is Mr. Fawcett. Enjoy the rest of your day.